Okay, excellent. Yeah.
All right. So it is 1 o'clock. So I am happy to introduce Dr. Patrick O'Neill from Texas A&M, who was previously a PhD student at Texas A&M and now he's a postdoc there. And he'll be speaking to us today about some research that he's been doing on MCMP data for machine learning. Patrick, take it away.
Excellent. Still very weird to hear Dr. Patrick O'Neill. It's still pretty new, but I really appreciate it. And I'm very excited to be here today presenting to quite a large audience. Hopefully, um, y'all find this informative. So let's jump right in. I'm going to give you a disclaimer off of the bat. Most of what we are going to talk about today is not going to be machine learning or ML. So I hope none of you feel too duped. It's mostly going to be about the data that we used in some of our research here at Texas A&M to make that ML happen. But still an interesting topic, I hope. So here's a little bit of an overview of how the talk's going to go. I'm going to introduce a nuclear forensics problem. You got to start with something catchy. After that, we'll do a little bit of a review of Monte Carlo. I know you guys had a lecture earlier this week on Monte Carlo, so just very quick, big ideas type hit, as well as introduce MCMP, which is a Monte Carlo a tool that uses Monte Carlo. We'll talk about some reactors that we modeled using MCMP, how we leverage that data in a machine learning context, and then how we also used MCMP to support some validation experiments. So getting right into it, I have a problem that I would like you to consider. So you get a call from someone who's having a bad day. Um, Maybe they're a scientist who works at a port or a border crossing, and something triggered a portal monitor or some sort of radiation detector. And upon further investigation, they determined it was a separated plutonium sample. So that could be a powderized oxide, could be a metal, but the person who's calling you needs to know with a certain amount of swiftness where that sample was produced because hopefully many of you know, but in case you don't, plutonium is not found in nature in abundance. So any appreciable quantity of it that appears in the world had to have been produced, and most likely it was produced in a nuclear reactor. Um, so some useful information that you could give this person who's calling you is what type of reactor the sample was produced in, the amount of time that the sample spent in that reactor, we'll call that the burnup or the sample burnup, and how long has it been since the sample was in that reactor, and we'll call that TSI or time since irradiation. And with those three pieces of information, um, there could be some educated guessing about the origins of where that plutonium's from. So a very scary situation to consider. Plutonium outside of regulatory control is nothing to laugh at. Um, and so it's important that if that ever were to happen, these three questions could be answered. So what is something that you could use to answer those questions? And one of those signatures that can be used is the isotopes within that plutonium sample. So my specific research used isotope ratios as our forensic signature of interest. And we considered both the plutonium vector, so considering different isotopes of plutonium, right? 239, 240, 241, 242, but also trace fission product contaminants. So when you do a separation, separating plutonium out from used nuclear fuel, even the best chemist in the world is not going to get 100% pure plutonium. There will be other things that come with that plutonium, and some fission products that are of note that we're interested in are cesiums, some bariums, some samariums, and some europiums. You can see those in the table on the right. So some criteria that we use to select these isotope ratios, had to be detectable, right? If you can't detect it, it's to you, it's not even there. So had to be something that during the irradiation, during the fuel cycle, that the the sample was in the fuel, it generated these fission products to a degree that once it's been separated and out in the wild, and you did some analysis, you could determine the quantity. And it also needed to be sufficiently long-lived that if you again found it outside of regulatory control, those fission products would still be there. They hadn't decayed away. We also use intra-element ratios. So you'll notice all those ratios are two of the same element, but just different isotopes. And that's to ensure that you don't have to make any assumptions about the conditions in which it was separated. So different elements are separated at different efficiencies, but all of those isotopes are going to be separated at the same efficiency because they're the same element. So what makes these isotope ratios useful for this problem? So there are kind of four mechanisms that are happening within a nuclear reactor that can produce these differences in isotope ratios when we consider our three problems or our three parameters that we're really interested in, right? The reactor type, the fuel burnup, and the time sensitive radiation. So the first two kind of go back to determining a reactor type. So there can be a discrepancy in isotope production depending on what energy spectrum the neutron flux in the reactor has. And you can kind of see an example of this in the samarium ratio plot on the bottom. That ratio is going to be much different for a generic PWR or a generic PHWR, which are a pressurized water reactor and pressurized heavy water reactor, than a generic fast breeder reactor or FBR. Because the PWR and PHWR have thermal flux spectrums, while the FBR has a fast spectrum. And if I lost anybody there, who maybe hasn't taken any kind of reactor physics class, like definitely drop something in the chat, and I'll clear that up. But other than that, I'm going to move on. When we talk about burnup, one of the mechanisms that we can use to determine different fuel burnups is when in those isotope ratios, the two constituents have a difference in how many neutrons it takes to produce those. So you can kind of see an example of this in the top plot with the europium ratio. Depending on how long that sample was in the reactor, if one of the constituents requires more neutrons to be produced, so it's not a direct fission product, maybe it's a direct fission product that has to absorb an extra neutron to become that isotope versus a direct fission product. One of those constituents requires one neutron to be produced. One of those constituents requires two. And so as the burnup evolves, they'll grow at different rates. And you get a function that you can essentially, look at your curve and say, okay, this is what my ratio is. This is probably the corresponding burnup, right? And then the last is for determining TSI. I think this is the most intuitive. When two isotopes are decaying at different rates, if you have an idea of the starting burnup, you can back calculate to determine what the time has elapsed since that sample was in a reactor. So now that we know what we want to solve, the information that we're using to solve that, and why that information is useful for solving that problem, we need something that actually gets us from the isotope ratios, the signature that we have, to an answer. And for that, we're going to use ML. But it's important when we think about this to determine the scope that we care about. So, we have three parameters of interest. We have a list of reactor types. Right now, I'm going to keep it basic with just the generic pressurized water reactor, generic pressurized heavy water reactor, and generic fast breeder reactor, which I'll talk about in a little bit more detail later in the talk. But we have to also limit, what burnups do we care about and what TSIs do we care about. So the TSI is from 0 to 5,000 days. And the burnup, this is really important, is from 0 to 5 gigawatt days per MTU. This is a very low burnup. An average light water fuel assembly, so like from a PWR or a BWR, is going to reach a much higher burnup during its course of being fuel within a reactor. So why do we care about this super low burnup range? So um, a definition for you that you might not be aware of is there's different grades of plutonium. So there's weapons grade and there's reactor grade. Sometimes you see it as fuel grade. Weapons grade plutonium is defined as containing less than 7% Pu-240. You could also think of it as at least 94% Pu-239. And the reason for this is Pu-240 is a heavy spontaneous fission neutron source. So it would be difficult to make a weapon with a sample of plutonium that has a high percentage of Pu-240. And if you aren't familiar with how plutonium is produced, I have a little bit of just a small diagram at the bottom that shows the primary method of production of Pu-239. There's an N gamma and a couple of beta decays, and you're there. And it should be noted that for the higher isotopes of plutonium, so 240, 241, and 242, which is what we commonly see in samples from reactor fuel, those are produced by additional N gamma reactions on the Pu-239. So to get to Pu-240, you're producing Pu-239. That's why you can kind of see that to produce weapons grade plutonium, you need to be at very low burnups, because as you burn the fuel and produce more Pu-239, you're going to eventually produce more Pu-240, which then degrades the quality of the plutonium for an adversary. So that's why we care about this really low burnup range, which is a very important distinction to make. So we know the problem, we know what we're going to use to solve the problem. Now we need data. So where are we going to get the data to solve this problem? ML is data driven, and the predictions that we can make are really only as good as the data that you give it. And we have all these reactors that we care about. We have a full range of burnups and TSI, and as nuclear energy progresses, we're going to have even more reactor types. It would be really nice to have some plutonium samples to analyze and add to our data set so that we can train these ML models and make predictions. But to update a quote from Back to the Future, I'm sure that in 2054 plutonium is available in every corner drugstore, but it's in 2024 it's a little hard to come by. So we don't have access to plutonium samples that kind of fit the criteria that we care about. There's some data on different plutonium samples out there, but maybe they don't have all of the isotopes of interest that we care about. So we have to create our own data, right? And I'm going to leave you on a bit of a cliffhanger on how we do that, so that I can review a little bit of Monte Carlo and introduce you to MCMP. So I'm sure during the Monte Carlo talk earlier in the week, you were introduced to the concept of a random walk. Essentially, if you have knowledge of how different parts of a system will behave, and you have a random number generator, you can simulate processes over and over and over again to kind of arrive at an average behavior. And I think it's really helpful when you consider Monte Carlo to move away from something that has probably been drilled into you for most of your education, which is solving an equation and solving a problem are not the same thing. Solving an equation is a way to solve a problem, but there's other ways to solve problems. And Monte Carlo is one of those ways. Now, that's not to say there aren't equations within, using Monte Carlo to solve problems, but you're not setting up an equation, making assumptions, solving it, and then just saying, "Boop, here's my answer." So this picture is actually, I think, pretty cool. It's something I like to think about when I think of Monte Carlo. It is a device that's called a Fermiac. It was developed by Enrico Fermi, and it is a way to do Monte Carlo without a computer, specifically Monte Carlo for neutron transport. So the diagram that you see being drawn on is a scaled reactor schematic with different materials, and you can do these random walks by using a random number to sample a path length for your neutron, and setting a wheel setting on this trolley, um, and then you roll it as far as that wheel will allow you. And once you've stopped, then you resample a direction. Well, you resample a collision type, and then a direction, and then a path length. And so you see these lines are particles that have previously been simulated. You can see the one on the right escaped. The one on the left was absorbed in the outer region. And if you do this enough times, you can get an idea of how neutrons behave in this fairly simple system. Um, I would, I think this is very cool. I'm glad I did not have to do this to solve any Monte Carlo problems of my own. But I think it's interesting to see it laid out like that. Um, and just a little bit kind of more about how the random walk works. Um, you go on this journey where you sample a path length and a direction, and then um, you use this CDF, which is kind of all of the possible ways that a collision could occur, um, with different probabilities. And when you sample a random number, you basically divide your space from 0 to 1. Your random number is from 0 to 1, and you divide that space um, to correspond to those probabilities that different collision types occur. Um, and kind of you do this over and over and over again, and it can give you some knowledge of how systems behave, systems that are very complicated that you maybe wouldn't be able to set up an equation to solve deterministically. Um, so what is MCMP? So you can see this diagram in the top right is kind of a graphical history of MCMP and all of the things that have gone into it. Um, MCMP stands for Monte Carlo N particle. Um, it's a continuous energy and generalized geometry method for doing particle transport. These are important to note. It's pretty much anytime you see anybody write about MCMP, these are the first two things they mention. And the reason they mention them and why they're really important, continuous energy is kind of the leg up that Monte Carlo has on deterministic methods. So when you solve an equation, you will have to make usually some sort of discretization uh, on the particle energies, bin them, and then solve for all the bins, and solve your problem that way. And generalized geometry is something that really sets MCMP apart from many other Monte Carlo methods. It really makes it super versatile because you can make anything with the geometry in MCMP. It seems like it's really a great number of possibilities of the things you can do with the geometry kind of tools that you have in MCMP. So it's developed and maintained by Los Alamos National Lab. And some of the strengths I already kind of alluded to. One is that versatility. The second is it has so many features because it's been developed for such a long time. In another presentation I've seen about MCMP, it's kind of, you can make an argument that it's the longest continuously developed code in the world, because they started developing the progenitor of MCMP in like the 1940s and 50s, and they just kept adding different features, and you can kind of see it, all those arrows that go into the main timeline of different features that they added because they kept developing their own Monte Carlo codes at LANL, and then they developed one for photons and shielding calculations and criticality calculations, and then they kept being like, oh, we can commingle these so that you can do all sorts of different problems under kind of the same roof. And it's also got a large community of users. There's a lot of documentation out there. And the code has been pretty rigorously validated just because it's been around so long and so many people use it. So when you go in a presentation and you say, hey, I used MCMP to do this thing, people are going to kind of trust that, right? Assuming that you've set everything up correctly, that's on you. But the code, there's some amount of trust you can have in it. The weakness, and this is a weakness of many Monte Carlo codes, is it is computationally intensive. It takes, when you have really complicated problems, it takes a long time, or it takes a pretty heavy duty computer, or if it's a really really complicated problem, both. So that's kind of, maybe if you have like a really simple system, and you can solve it in a different way, that might be something to look at. But for real world, complicated systems, it's a very good tool. So there's two primary modes that people use MCMP in, and there's a lot of bells and whistles. I'm not going to talk about all of them, but the two kind of primary ways that people use MCMP to solve problems is, one is source defined problems, and this can be a variety of different particles or ions that are being emitted from a variety of different types of sources. You could have point sources, surface sources, uh, you know, box sources, spherical sources. It's again, there's a lot of flexibility, and so this is really useful for if you're calculating dosimetry, shielding, you're designing a detector. Um, I mean, I could list a lot of things here, so I just kind of picked three that are pretty big, right? Um, and the output you get from a source-driven problem, is a tally type that you designate. And there's also flexibility in your tallies. Maybe you just care about, hey, how many neutrons are coming through this wall that's next to an experimental facility? Or how much energy are these gammas depositing into the detector's, volume of interest? So that's just an example of two, but there's really a lot of different, a lot of different tallies that you can use to solve different types of problems. The other primary mode that people use is called K code or criticality. This is neutrons only, but this is how you do a lot of reactor physics and crit safety. You're basically solving for the K effective or the criticality of the system. Um, and if you've been paying attention to kind of the first part of this talk, you know that I care about isotopes and isotopic compositions and isotope ratios, and neither of these outputs are isotopic values, right? So why do I, love MCMP so much to be kind of the engine that produces all this data for my problem? Well, one of the capabilities that got folded into MCMP a long time ago was the ability to do depletion or burnup calculations. So MCMP actually uses a separate module that's called Cinder 90 to deplete nuclides. Cinder 90 actually, fun fact, was not developed at LANL. It was developed initially, I believe, at Bettis Lab. And it's called Cinder 90 because that edition of Cinder, I mean, they started developing it in like the 60s, but Cinder 90 uh, was produced in the 90s, like many great things. Um, but how Cinder 90 works is first, MCMP will perform a K code calculation. Um, and so that will give the user an idea of the flux of your system, the neutron flux of your system. And using that neutron flux, you can produce reaction rates for all the nuclides that you care about over the time step that you have designated. And basically what Cinder 90 does is it's kind of it iterates over these time steps. First MCMP does a calculation, then it gives its reaction rates to Cinder 90, and then Cinder 90 gives back reactor materials, and then you perform a new K code calculation and get new reaction rates, and so on and so forth until MCMP and Cinder 90 have gone through all of the time steps that you care about. You could do this yourself if you wanted. You don't have to use Cinder 90. You could just run your own K code calculations, update your materials, create a new MCMP deck, and run it again. But it's really nice that MCMP has a module that does it for you, because depending on how many nuclides you care about, that could get really messy really fast. So a little bit more about how Cinder 90 works. Maybe this graphical kind of representation can help a little bit. I know it's a little bit busy. But first we got to start with what does Cinder 90 do? So Cinder 90 is not using Monte Carlo. It's taking data from, an output from Monte Carlo, but the actual calculation that Cinder 90 does is deterministic. And what you're solving are these Bateman equations that you can see at the top. which is a differential equation describing the rate of change of a nuclide concentration. So the first term is your loss term, that negative Ni as a function of time times beta I. This is basically how your population of interest is being removed. So in the case of a reactor operating, that could be a neutron interacting with your nuclide of interest and then it's transmuting, or it could be it naturally decaying. The Y bar term is kind of an external uh, like source of this nuclide. And then the last term is a gain term related to what is transmuting or what nuclear processes are producing your nuclide of interest. So that could be, if it's a fission product, what's the fission reaction rate times the yield of the nuclide that you're interested in, or maybe it's something else in the reactor is decaying to the nuclide of interest, or maybe there is another nuclide that when interacted with by a neutron um, will produce the nuclide of interest. So kind of as I alluded to, if you were to do this kind of by yourself, you have to keep track of a lot of different isotopes in order to have accurate uh, accurate estimates of different isotopic concentrations. The assumption that's being made in Cinder 90, and this is really important from a user standpoint, is the reaction rate, sorry, that should say reaction rate, is assumed to be constant throughout the burn step, which means as a user, you have to select burn steps where that will be true. So for example, when you're doing the initial burn steps for a large power reactor, um, there are certain isotopes that are fission products that will have act as a neutron poison within the core. And so you have to pick burn steps that are small enough that you accurately account for the buildup of those poisons, mostly xenon. Xenon is really, really important when you're talking about starting a large power reactor. But yeah, I kind of talked about the way that MCMP and Cinder 90 interact. This is a graphical way to depict that. So we're starting on the left with MCMP doing a K-code calculation at time t equals 0. It produces reaction rates that it gives to Cinder 90, and it solves the Bateman equations to get updated material compositions for time t1. And kind of as an extra check to make sure that this assumption is holding, um, what it does, that first step is called the predictor step, and now it does what's called the corrector step. So it goes back to time t 1/2. It gives the updated materials to MCMP because the materials are going to change your K-code calculation. It reruns the K-code calculation, and then it corrects the reaction rates, gives it back to Cinder 90, resolves the Bateman equations. So now you have updated uh, materials again. It does kind of an averaging between the predictor and the corrector step, and then it feeds those updated materials to MCMP again to run the next time steps to move on to moving from T1 to T2. And again, it's uh, solving a pretty simple equation, just solving it a lot of times for a lot of different materials, and then doing this communication. And Cinder 90 makes your life a lot easier than maybe it would be if they had not added that feature to MCMP. Also, I should note this takes a long time to run or it can for complicated systems, because for every burn step, you basically you have double the amount of burn steps that than you list, right? Because you do everything twice. You do that predictor step and then the corrector step. So now that we've kind of talked about what Monte Carlo is and why we're using MCMP and what we're specifically using MCMP to do, let's talk about some reactors that we modeled using MCMP as to form the kind of the backbone for our nuclear forensics method. So the first one is a pressurized water reactor model. You can see a depiction of the assembly in MCMP on the right. I'm sorry that the lines get a little blurry. MCMP is a great code, but it's visualization. Uh, some of its capabilities could be a little bit better. This is also pretty old, so I mean they might have improved it in later versions, the kind of the internal plotters and such. But the blue are fuel pins. The red is light water that's acting as both a coolant and a moderator, and the green are guide tubes. So in reality, when you do a core model, some of those guide tubes will actually be control elements, but this is just without any control elements, just what it will look like with just guide tubes. Um, so this model that we used in our research, I should also, well, before, I have a confession to make before we go through all these models. I used all the data from these models, but I actually didn't write any of them. So I stand on the shoulders of giants in terms of other PhD students who came before me and kind of paved the way for me. I mean, I could have done these. I am a proficient MCMP user, and in my master's work, I modeled all sorts of different systems. But we already had this data, and I was just very fortunate to kind of apply it in a pretty cool way. So a PWR is this one is based on an AP1000 design. It's a thermal spectrum at 3,400 megawatts thermal. Um, and the data was taken from a simulation that was actually an entire core simulation. So it wasn't an assembly simulation, it was an entire core. And the AP1000 is fueled at three different enrichment zones, 2.35, 3.4, and 4.45 weight percent of U-235. And the isotopic data that we used in our models were taken from the 3.4 weight percent fuel enrichment zone. One of the things that maybe could be future work is including more of those enrichment zones and seeing how challenging it might be to make nuclear forensics determination when you have kind of two fairly similar or three fairly similar reactor types, between all these enrichment zones. Another reactor that we modeled was a pressurized heavy water reactor. This is similar to a CANDU reactor, which are the CAN and CANDU is for Canada. So these are common up there. Although this CANDU that we modeled was based on an Indian design. So the CANDU is fueled with naturally enriched UO2. It also has a thermal spectrum, but the CANDU uses heavy water as its moderator and primary coolant versus the light water reactor. The PWR is a light water reactor. This is a heavy water reactor. And it's got a pretty interesting design that allows for online refueling. So the fuel bundle that you can see, the pink is your fuel. They're cylindrical rods. They're not spheres. They are in a pressure tube. And those pressure tubes can actually be taken out of the core without shutting the entire core down like you would have to do for a PWR. And the power for this one was 756 megawatts thermal. And our MCMP model for this was just one fuel bundle, but with a reflective boundary condition. So yeah, moving on, another that we've kind of discussed is a fast breeder reactor. This is based on the Indian PFBR. This one's a little bit different from the other two because it's a fast spectrum reactor. So we don't care about moderating the neutrons in this one. Power is 1250 megawatts thermal. It's cooled with liquid sodium, so moving away from water. And there's actually three core regions. You can see a core model on the right. There's two inner core regions that have driver fuel that's MOX or mixed oxide. So that's not just UO2, that's UO2, but also plutonium, PuO2. And there's also a blanket region of depleted UO2, which is where you're actually breeding more plutonium, which then you reprocess and you fabricate into MOX. And so the full core was modeled for our purposes, but all of our isotopic data was taken from that depleted UO2 blanket region. And just something to highlight, so these are what the fuel arrangements look like for both the core and the radial blanket. And I wanted to show it because you can see these are much more tightly packed than the other two reactors, and that's because your primary kind of design consideration in a fast reactor is to limit the leakage of neutrons. So you want your fuel to be as close together as possible while still being able to maintain your safety margin and cool it effectively. So those were three reactors that we modeled, and there's some more that we modeled, but for simplicity's sake, I'm leaving them out. Um, and we took that data and we leveraged it for ML. So the first thing is we have all this data. How are we going to give it to our models? So um, this is just a way I like to visualize generating those training data sets. Basically randomly sampling over our entire domain of interest that we talked about before, 0 to 5,000 TSI, 0 to 5 gigawatt days per MTU. And then we have all these isotope ratios that we care about, and some reactor types that we care about. The astute figure viewer might notice there's two reactor types I haven't talked about yet, and I'm going to talk about them in a sec. So how does this training data set, what kind of models are we using? How are we feeding it to our models to produce the predictions that we care about? So I have a flow sheet of kind of how our forensics methodology works, and unfortunately, I don't really have time to go into like what these ML models, what they kind of mean. I have some backup slides. We can talk about it in questions if that's like a burning people really want to know. But for right now, we're just the most important thing from this very busy flow sheet is we actually, we have three things that we care about. We actually separate it into three different steps. So the first step is and kind of so on this kind of the second level of boxes down and on the right is we do our reactor classification first. And the type of model we use for that is called a support vector machine. And the kernel that we use is a qubit kernel. Support vector machines are basically an optimized way to draw decision boundaries by taking into account how to maximize the margin between different groups that you're trying to classify. So this is a classification problem where your number or your answer is not going to be a number; it's going to be a class. So FBR or PWR, something like that. After we've determined a reactor type, we have a set of burnup quantification models that we use. So for each different reactor type, it has its own burnup quantifier. These types of models are Gaussian process regression models, and they use exponential kernels. And then after we've determined a reactor class and a predicted burnup, we can actually do our TSI calculation analytically using our cesium 134 to 137 because we know what the concentration is right now. We know what the concentration should have been based on our MCMP data. And from there, we can, and we know the half-lives, so we can find the time that's elapsed. And those are the three things that we care about. So when we kind of train these models and we test them using the MCMP data, we get good performance. I'm not going to go too much into the performance, but I am going to talk about something that's really important to do when you have methods that are primarily simulation based, right? Which is to perform validation experiments. So and MCMP supported our validation experiments. So what do I mean by validation experiments? We went the people I work with. I didn't actually get to be in on these experiments too much from the lab setting, but I did use the data again, and I'm very thankful to the people who did these experiments. So what our lab group did is we took different UO2 samples. We sent them to research reactors. We irradiated them. We brought them back. We separated them, and then we characterized the plutonium and all the different isotopes within that plutonium to see if our methods could make accurate predictions with a sample that's physical and real. This is pretty unique. Not a lot of universities get to separate their own plutonium. And we get to do it here at Texas A&M, which is pretty amazing. So the first validation experiment we did was at HIFER, which is the high flux isotope reactor at Oak Ridge National Lab. And this one is a little bit more unique than the other two experiments I'm going to talk about. So um, the intent for this experiment was to emulate what you might see in the blanket region of an FBR. So irradiating depleted UO2. The only problem is HIFER is a thermal reactor, and the FBR is obviously a fast reactor. So what was done in the sample preparation stage to emulate that FBR was the sample was sheathed in gadolinium. Gadolinium has a good thermal neutron absorbance cross section. So effectively, by making sure that the sample is not being exposed to thermal neutrons, it's being exposed to a faster flux, kind of trying to do a little bit of emulation of what might be happening in an FBR blanket region. Unfortunately, um, these the sample was intended to only reach a burnup of 1 gigawatt day roughly per MTU. Due to just the facility operations, it received a burnup of 4.36 gigawatt days per MTU, completely depleting the gadolinium. So halfway through this irradiation, suddenly the sample was seeing a large thermal flux. So this is a sample that's pretty unique in that um, it was irradiated in a kind of an epithermal flux. It was irradiated in a thermal flux, and it has some pretty wacky behavior as a result. But the way that we use MCMP to support these, so for one, we have to produce MCMP data that we can then give to our ML models, right? So we have to kind of treat it the same as those generic power reactors I was talking about. But two, before we send a sample off to a research reactor, they want to know, hey, how long do you want it to be in the core? And we have specific burnups that we're targeting. So we ask them about where it's going to be placed and what kind of packaging it's going to be in, and then we can model that burnup and just see, okay, approximately what amount of time do we want it to be in the core to reach the conditions that we want it to be at. So MCMP is really helping kind of in two different areas when we consider this validation data. So we did two other samples, both of them at MUR, which is the Missouri University Research Reactor at the University of Missouri. MUR is also has a thermal spectrum. You can see kind of pictures of a slice of the core if you have radial symmetry. You don't have to do a full core model. You can model a part that will be symmetric. It saves you some computation time. So in this case, the sample irradiation position was in the graphite reflector region. It's not denoted on the top-down view that's on the left, but it is on the axial view on the right. You can kind of see it's up near the top and sort of right as you start to get into the graphite reflector region. This first experiment at MUR was meant to emulate a CANDU reactor, so an actual UO2 sample irradiated in a thermal flux spectrum. And then we did another one at MUR, but this time with LeO2, so low enriched UO2, in this case 3.44 weight percent, which is meant to emulate that PWR that we talked about. So now we don't just have three predictable classes, we've moved to 6 predictable classes, and each of these samples has kind of unique characteristics, and can our methodology that uses these ML models and all this MCMP data, will it be able to correctly predict when we give it data from an actual sample that we irradiated in a reactor, got it back, separated out the plutonium, and these are some of the results that we've published in literature. So for HIFER and this MER case, which is the MER natural, when we did this paper, we only had the MER natural. We didn't have the MER 344 yet. So this is HIFER and MER natural. You can see, first, I didn't put it on this slide, but the samples were accurately predicted by the ML model to belong to the HIFER and the MER natural classes. And you can also see the predictions of burnup and TSI compared to the measured values. They are not exactly the same. Obviously, there's going to be a little bit of difference between simulation and reality, um, but they are close enough that if you were presented with that question on the first slide, you would be giving accurate information to a decision maker, and that's what really matters for this. They were compared against a legacy method that used the maximum likelihood formulation to relate the isotope ratios to the parameters that we care about. Um, and we like the maximum likelihood. This isn't like, obviously from these tables, the machine learning is not dunking on the maximum likelihood. Um, this study was meant to see if we could emulate that success, because there's some additional work that we did down the line where the machine learning was just a little bit better suited. So we wanted to make sure that it was meeting the benchmarks we had already established. So the MER 344, you can see I actually do have prediction scores here. Um, and I also have a little bit more kind of analysis of which isotope ratios, uh, inclusions, helped predictions or hurt predictions, and kind of some of the associated uncertainties that we have with these predictions. A little bit more detail. Again, both of these results are in open literature, and you can read a lot more about them. But the big takeaway from this slide is that the MER 344, we could correctly attribute the highest scores are those zeros, all the other scores are negative. Even when we dropped out certain isotopes, we did that because of high experimental uncertainty when we characterized the isotope ratios. So measurement uncertainty, sorry, not experimental uncertainty. We were able to accurately predict TSI of 448 days, so only off by 1 day. Pretty nice. And the burn up, we had to massage a little bit which isotope ratios we were using. Um, the main takeaway there was we had to exclude the cesium 134 to 137 because when we were doing our characterization of the sample, we had some interference in the way that we measured that. So that isotope ratio was actually just completely off. And you can see it was actually throwing off our ability to predict burnup um, quite heavily. All of the two predictions that include that cesium, so the full ratio set, and only excluding europium 154 to 155, we were much farther off. Again, I should remind you, the measured is right around a little bit under 1 gigawatt day per MTU. So with that, I've kind of gone through a lot of different stuff, right? So I just wanted to leave you with a couple of big picture thoughts. The first, and I hope this is the biggest takeaway, the quality of your data is important. This is true for Monte Carlo. Monte Carlo depends on quality cross sections. We didn't really talk about that a whole ton, but when you think about that like random walk, the only information you're really giving to it that's unique to your problem is your interaction cross sections. So data is really, really important for both Monte Carlo, and luckily, we've been doing Monte Carlo for a long time, and we have data that kind of as a community, there's a consensus that we can somewhat trust it. But data is also really important for data-driven methods like these simple ML models that I'm using. Um, Another takeaway, kind of because this is a summer school, the things you learn in class can contribute to your problems, right? There's a lot of different core nuclear engineering concepts that are coming together in this type of problem. Reactor physics, radiochemistry. I'm sure there was other talks that you heard this summer where, for some of those detector, people who do a lot more research around radiation detection, there are so many different areas of nuclear engineering that kind of contribute to those research efforts. So pay attention in class. um, and also, every time I use MCMP, I just think about how lucky I am to live in a time where we have such abundant computational resources. I am very glad I'm not drawing lines myself on a 2D plot. That is definitely would have been a graduate student type job back in the day. I'm glad that my graduate education was not having to do that. It was just having to be mad at my computer and in essence mad at myself. I want to thank the people I collaborated with and people who contributed to this work before I started. So Dr. Sunil Chirioth was my advisor. He is no longer at Texas A&M. He took a position at Oak Ridge National Lab. And I'd like to thank Doctors Jeremy Osborne and Matthew Sweeney, who were PhD students before me, who did a lot of the legwork that I kind of talked about, as well as Dr. Sean Martinson, who is somebody I actively collaborated with at A&M, who he did the last MER sample. He did that characterization, and very talented scientist that I'm very lucky I got to work with. And I'd also like to thank the people who funded some of this research, and who, put on this great summer school that I'm very pleased to be giving a lecture for, the MTV consortium. So with that, I think uh, we have some time for some questions. I meant to finish like 5 minutes earlier so we could have a lot of time for questions, but hey, that's how it goes. So yeah.
Well, thank you, Patrick. That was really interesting. I really enjoyed that. So we do have some questions that are coming through on the chat. Um, so I think the first one is machine learning really necessary? I think you answered this one, but I wanted to know if there was anything more that you wanted to say about it. So, is machine learning really necessary? Solving for the few origin data parameters given a number of ratio data points sounds more like simultaneous equation slash matrix multiplication, or is that an oversimplification? I think you addressed some of this question. I didn't know if there was anything more that you wanted to say about that one.
Yeah, I would just say there's a lot of ways to skin that problem. We went with ML. Again, there was a statistical kind of approach that was just looking at doing a maximum likelihood calculation. The things I like about ML specifically for this is the speed. So like once you've trained your models, you can just rip through predictions. The other thing I like um, is I like that you can deconvolute the problem into, I have three things I care about. I have three different models that do those things instead of some other approaches you kind of have to solve for all three things at the same time. And I like the way that ML worked out for that. And when we initially chose to go down this ML route, we actually weren't 100% sure that we were going to stick with it. It was just something to try, and it ended up working out. I should also note one of the things I kind of alluded to about why we moved from the maximum likelihood approach to an ML approach, that I didn't get to talk about in this talk just because it would have been way too much, was the real crux of my dissertation was actually analyzing samples that contained a mixture of plutonium from multiple different reactor type sources. So like say you had a sample that was 30% of the sample was produced in an FBR, and 30% or 70% was produced in a CANDU, or a PHWR. Sorry, I gotta stick with my the nomenclature I already set up. And when you move to that, you can get some really, really complicated databases. You end up with a lot of data. And so I wanted to do something that was I wanted to use machine learning for that to see if it could do it. So yeah, no, that's an astute question though.
Excellent. Thank you. So the next question is, in terms of computational complexity weakness of MCMP, is it asymptotically convergent, asymptotically convergent? If yes, what's its big O estimate?
I am not a computer scientist, so I'm bad at these types of questions. I will say, one of the nice things about uh, MCMP is, uh, I mean, the computational demands are really related to how complicated your problem is and how good you want your statistics to be. So you really only start to run into big issues when you're running a lot of different, you want to run the same problem a bunch of different times. You really need to care about your run times. Or if your problem is really complex, you really have to care about your run times. But MCMP, another advantage I didn't really get to talk about, that I should have talked about, is it does have some pretty robust ways to do variance reduction so that even with pretty complicated problems, you can reduce some of your runtime. So I don't have a good answer for that. I'm a user of MCMP. I'm not a developer of MCMP, so I don't think about those things. I think about, oh, I need to run this. Is this going to take an hour? Is this going to take a day? Or is this going to take a week? And it really depends on your problem. So, or multiple weeks, depending. So I'm really sorry I don't have a good answer for that.
I tried looking it up as well and couldn't find anything easily available, and I didn't know. But
Yeah, and I
your
will
ins
say, I will say part of like the reason there's not a great answer for that is there's so many different things MCMP does that, like, if you're talking about a burn calculation, if you're talking about, you know, uh, a calculation involving photons that are bouncing around a ton, is really going to change your answer.
I think your answer for the previous question answers the next question quite well.
Oh,
As what is the runtime for one generation of this MCNP Cinder 90 simulation?
yeah.
It
So
seems to be it depends.
yeah, it depends on how big your reactor is. So that's like one of the reasons, like when you can get away with running an assembly versus a full core, you want to run the assembly because it's going to be a lot faster. So yeah, it just depends on, again, those statistics, how many particles you're running. So when you run a K code calculation, you designate, like, I want to run X amount of particles, I want to skip this many cycles, I want to do this many cycles. So um, the devil is just in how many times you're kind of doing the same things over and over again. Um, so that's kind of what really adds up. But I would say and it depends on what, how many another nice thing about MCMP is, it's been parallelized, especially for stuff like burn calculations. So it really depends on like the size of computer you're running on, and how complicated your problem is, what kind of statistics you want, how many burn steps, how big are the burn steps. But yeah, I mean, some of the gnarlier stuff I've done has been like on the order of weeks. And those aren't even, I personally haven't had to do some of the more complicated, like once you get into like there's like thousands of cells. Ooh, yeah, it's could get. I also haven't had access to like any really, really super powerful computers. I have access to the departmental ones at A&M, which they've always been great for me, and I really appreciate them. I'm not disparaging them, but I know when you're at a national lab, there's some pretty heavy hitters in terms of cores and computation time. So
A little bit different from computation time. So the following question was that the person asking is familiar with K code given K effective, but for a power reactor, wouldn't the K effective of the system be kept at 1 by control rods, while you could have different neutron flux depending on power level? How does K code get to a neutron flux for the Cinder inventory solve?
yeah, so it really it depends on if you configure. So you can configure your reactor with control rods in or control rods out, and that will obviously change the calculation. Um, the big thing really is for burn up, when you think about it, um, small variations in K are really not going to kill you. So you really just have to designate a power. The big thing is the power is uh, and that will kind of dictate, yeah, uh, if at this power you have a K of 1 or a little above 1, depending on, it's like if you are kind of running without control rods in, and in the real world you'd have control rods in and be at 1. It's really about uh, that flux isn't like, doesn't need to be so fine, right? For a large power reactor, um, you need to kind of you have to think about the scales of the problem, right? When you're talking about, these variations in flux might affect like a very low, like a very small digit in your final isotope um, uh, concentration. So yeah, you're really just using um, you're really using the power level that you designate on your burn card to correctly scale the K answer that you get to. I don't think that was a very good answer. I'm sorry. It's something I've actually never really thought about. It's just you run K code, you give it power, you give burn steps, and it does the work. So sorry.
All right. Well, that puts us right at 2 o'clock. So, and out of respect for your time, Patrick, I wanted to say thank you so much for being here, for answering all of the questions. It was a really great talk. For everybody listening, this should be available on the summer school website over the next couple of days. If anybody is interested in rewatching, thank you so much. And we'll see you back here next week.
All right, thanks for having me. You guys have a great day.
Thanks, Patrick.